Andrea Majorana from Istituto Superiore di Sanità in Italy, and he will speak about contribution of local geology, anthropogenic sources and building materials on the radon exposure in dwellings, modeling and experimentation.
So, good morning, everyone. And today we will show you some results about about work package 2. And in particular, I will talk to you about some results in subtask 2.3.1. So we are talking about building materials as a source of indoor radon exposure. Some outlines about my presentation. We will talk about the state of art of radon exhalation rate measurements from building materials. Then we will have a summary of the models to assess indoor radon activity concentration, especially from building materials contribution. And then we will see 3 different approaches to measure radon exhalation rate from building materials. So a theoretical approach, then a direct approach of measurement. And in particular, we will see that thanks to Radonorm, we were able to perform a lot of measurements in situ. And we will see also some preliminary results on these measurements and also a short discussion about it. And then we will have a part dedicated to a comparison between radon exhalation rate measured on the sample and radon exhalation rate measured directly from building structures. And then some short conclusions. Okay, regarding the state of the art, we can see that we know very well that a last council directive requires to consider any source of radon, including building materials. And it's important to assess the radon exhalation rate from building materials, both for preventive and for remedial intervention to reduce population exposure to radon. Then we know that according to the current state of knowledge and technology, the radon exhalation rate from building structure may be estimated through 3 different approaches. So modeling of the radon transport inside the structure. So by solving we can see a radon transport equation in porous matrix. Then the second approach is to model the correlation between the radon exhalation rate measured on building material samples and the radon exhalation rate occurring, actually exhaling from a building structure made of that material. And then the third approach, the last one, is to measure directly the radon exhalation rate from the manufacture. So here we have a table that is also reported, of course, in our milestone. It is a synthesis of which are the main advantages and disadvantages of each approach. So in the first line, you can see, okay, no last. You can see the references for each one of the 3 approaches. Then in the second line, the advantages and then the limits. Regarding the modeling of the radon transport inside the structure, so the theoretical approach, the main advantages are that there are no difficulties related to experimental measurements, and it is the only approach feasible in preventive strategies when the building structure is not yet built. The main limits of this first approach is that a wide dataset of input parameters is required, of course, to characterize the exhaling manufacture, and the influence of installation conditions and environmental parameters are not considered, of course, because they are very specific of the case scenario. The second approach to model the correlation with the radon exhalation rate from a building material sample is very useful because we can have measurements that are feasible and well documented in literature. But the main limits of this approach, that is also the most used, is that there is only one model to correlate the radon exhalation rate measured on the sample to that occurring inside from a building manufacture, so for example from a wall. Then the requirement of the availability of a sample representative for that building structure, for that wall, that is not very simple because in a lot of circumstances you are forced to destroy the wall to take these samples. And then the last limit is that the advective radon transport in this case is neglected because the difference of pressure occurring in situ in a wall, it is not considered in laboratory when you perform this measurement. And then we have the last approach, so the direct measurement of the radon exhalation rate from the manufacture. And we can say that the main advantages of this approach are that the influence of installation conditions and environmental parameters are considered because you are measuring the radon exhalation rate on site. The advective transport is also considered because for the same reason, because you are on site. But in this case, there are many limits, mainly related to the engineering part, we can say, because you need to assure the air tightness of the system when you perform this measurement on the wall. So you need to perform this measurement to assure the air tightness of the system without damaging the wall or the building structure considered. And we will now see specifically each one of these three approaches and what we have done within the Radonor project and which are the main results. In the milestone, you can find also a summary of the models to assess indoor radon activity concentration. So to pass from the buildings, the radon exhalation rate from building structure to the radon activity concentration indoor. So in a room, in a dwelling. And you can in particular find three different we decided to divide them into analytical models, compartment models, and software considering detailed physical processes. But you can find all of these in the milestone. So the first approach is the theoretical one, and we developed in particular a lot of solutions, a lot of formulation to estimate radon exhalation rate, divided into different models, so considering or not diffusive radon transport and advective radon transport. And we developed this solution in particular for three case specific. We can say three boundary conditions that are described here as the letter A, letter B, and letter C. So fixed radon concentration on both sides of affinity slab, fixed radon concentration only on one side of the wall of our slab, or the third case is a wall, a building structure in an environment with a uniform radon concentration, so with similar radon concentration on both sides of the wall. Pertaining to the models, we have decided to analyze 4 different models, considering or not the inner radon generation, and considering or not the advective radon transport. For each one of this case, we have developed a formulation, so to assess radon exhalation rate, starting from, of course, input parameters, different input parameters, and all these results are reported in milestone. Pertaining to the direct measurement of the radon exhalation rate from a building structure, an experimental apparatus named Siren was developed at our laboratory. It is the only existing apparatus, the first one developed to perform non-destructive measurement of radon exhalation rate from vertical surfaces. And it has, of course, some characteristics. It is self-sustaining, transportable, adjustable. It is capable to perform non-destructive measurements, and it is consistent with any continuous radon monitors. Here you can see an image of this apparatus. And of course, we have also commissioned this apparatus, in particular on air tightness and repeatability of the measurements. Okay, here we have another photo of the apparatus during the measurements. Pertaining to the activities of in situ measurement with SIREN within a radon project, we have employed it to measure the radon exhalation rate from some building manufacts. We can see here an image. So the walls were made of a very common building material in central Italy, that is Italian red tuff with black scoria. A lot of cities in central Italy are made of these building materials, which has high radium-226 content, as we can see here, about between 200 and 300. But so it is a very big problem relating to radon exhalation rate, of course. And the results of these measurements were in particularly related to different superficial finishing of these walls. So we have decided to take these building material samples to build a wall, and then the quality of the superficial finishing was increased time by time. So we have a first configuration with a rough wall, only blocks bound by mortar, then an intermediate wall, a plastered wall, and a painted wall. And we had a lot of results on radon exhalation rate on each one of these configuration. Here you can see SIREN during the measurements, and of course the painted wall is the typical scenario in dwellings. So these are the preliminary results on wall superficial finishing. So for both walls, the addition of mortar reduces the losses of the measuring apparatus, and therefore we can see the radon exhalation rate to increase. Then regarding the addition of plaster, we can see a reduction of about 10% of radon exhalation rate, because it is an additional layer partially obstacling the radon exhalation rate from the tough samples. And then adding a layer of paint reduces the radon exhalation rate of about 15%. So we can see this trend, and so the effect of this different wall superficial finishing on radon exhalation rate. Then regarding the wall dimension, because in the previous image you saw that we built two different walls of different dimensions, so one big and one small. And we noticed that no significant statistical differences occurred between big and small walls. You can see as the results are not showed not significant statistical differences. So the net radon transport occurs only perpendicularly to the wall surfaces, and in particular the coefficient of variation was very small, so ranged from 10 to 22% for big wall, and from 13 to 26% for the small one. Okay, now we have the big question. So how to relate the radon exhalation rate measured from a building material sample to that occurring in situ, so in a dwelling where people live, because most of the measurements are typically carried out on samples of building materials and not in situ. So we performed a lot of measurements on building material samples through the so-called accumulation method described by IAEA 474. We had a lot of results on radon exhalation rate measurements, and then we related it using the model proposed by Dr. Sao, which is a big model with a lot of input parameters, and the output of the model is the radon exhalation rate from a wall made of the same material. So we made this comparison within the work of the milestone. And it's also important to point out that the assumptions of this model, the three main assumptions of this model are that the building manufacture is made of one material. So Sao considered a building manufacture made of one material. And this is not exactly our case, because really in situ you have a building manufacture surely made of mortar also, not only building materials, to bind all elements. Then the wall separates two environments with similar radon concentration, and This is not typically the case occurring in a dwelling, but it was in our case, and no advective transport occurs. So I will show you the results in next slide. The last statement is that in Milestone, we also developed a protocol for radon exhalation rate measurement using the accumulation method. We are just right now finalizing the last things on this protocol, but it will be surely finished for the end of Radonorm. In particular, it was focused on the Thoron interference on this kind of measurements, and also the influence of the dimensions of these samples on this kind of measurements. The results to the previous question are reported in this graph. So we can see how the radon exhalation rate measurement performed on the building material sample is the first on the left, and it is very different from the radon exhalation rate measured directly on the wall in each one of the different configurations studied. So rough wall, intermediate wall, plastered wall, and painted wall. But much more interesting is that the value predicted with the model of SAO is really higher than that found actually, so that measured. And these can be explained in different ways. In different ways, we are still performing some experiments, but one of the main reasons is that I was talking to you before, so that the wall of SAO is a wall made of only one material, while actually the walls of a dwellings or a typical scenario are made not only of one material, but of more material with some discontinuities between them. So for example, the mortar to keep the blocks binded together. So conclusions, the wall dimensions does not influence the measured radon exhalation rate from the wall surfaces. Increasing the quality of the wall superficial finishing reflects on the increase of measured radon exhalation rate due to possible losses. Adding a layer of plaster or paint leads to a reduction of measured radon exhalation rate of about 10 and 20% respectively. The difference between radon exhalation rate measured on the sample and measured direct on the wall is very significant, higher than 100%. And the only model to correlate the radon exhalation rate measured on a sample to that actually occurring in site resulted in a significant overestimations. More materials, of course, are currently being tested because I only talked to you about this Italian tuff, but we are developing the same results for other materials, so other kind of tuff, but also concrete with normal additions, and the results will be surely presented in next months. So thank you for your attention, and I am here for questions, but before questions, I think that Geraldine, my colleague, will present you the second part of the presentation, because I see her.
Geraldine, can you please share your presentation? Okay. What? Ah, oops.
No, perché è stessa.
Aspetta un po'.
Questa qui.
No, I'm lost.
Chiudi direttamente quella, se chiudi questa qua si dovrebbe levare, chiudi questa. Vedi.
We can see the first slide of Geraldine's presentation.
You can see?
Yeah.
Oh,
Un po' qua
ok.
su Webex. Ecco qua, un po' qua.
At least from Rome.
Questa, ecco.
Okay, now should work here as well. Thank you.
I think we can't hear you.
Yes, Geraldine, you should unmute your.
Can you hear me now?
Okay.
Yes.
Yes. Okay. It's okay. Thank you.
So good morning, everyone. So I will continue the presentation, and Ala, my colleague, will then continue and for the final part. The second part of the presentation is about another study we did for the subtask 2.3.3, and I present you this work on behalf of the co-authors you have here for this report we produced for the deliverable 2.8. So you can have more details about this study in this report. And the objective was to develop an approach to determine the contributions of local geology, but also other sources on the radon exposure in dwellings. And we will talk about modeling and different scenarios we applied to model radon transport from soils to indoor air. So the radiological protection issue that was our interest to test this approach was the following. Some situations showed that high radon levels in dwellings could be induced by local geology, but also by additional anthropogenic source resulting from human activity. And the objective was to provide some answers to questions that arise on exposure to radon in a building that may be due to the influence of both natural and anthropogenic sources, and for different typical situations. So we chose a case study to apply our modeling. This case study concerns typical situations that may be encountered in a particular context, in the context of the construction of dwellings on a repository of radium-bearing waste or uranium mill tailings, following the loss of the memory of the storages. So in this case study, it is also hypothesized that over time, the radium-bearing waste repositories currently monitored and maintained could be subject of a lack of monitoring following the loss of the memory of these facilities. And in this context, due to their location at the surface, it is not excluded that these sites may be the subject to development of, for example, the construction of buildings such as dwellings. So it is the context of the study. So the method we applied, it was only modeling. So modeling the transport of radon from the soil to the building in order to estimate the indoor radon concentration. And by defining different scenarios and by using the calculation tools that were existing within partners. So these tools are the following. The first is Tough2Radon that was developed at IRSN, and this code is based on the Tough2 software. I don't know if you already know this software. It is a US developed software, and we developed at IRSN a special module for numerical modeling of radon emanation and transport in soils. And this software was used to calculate the radon flux, the radon exhalation at the interface between the soil and the basement of the building. The second tool was applied was Matisse QAE, developed at the CSTB. And this software predicts the indoor air quality of buildings, and it can also assess the indoor radon exposure due to radon entry from the ground. And the last one applied was Indorad, developed at CIEMAT. And this is a dynamic model designed to estimate the radon concentration inside the buildings, taking into account changes of meteorological conditions. So we applied these three calculation tools. We defined different scenarios for modeling, and these scenarios were elaborated by using data available for an existing case. These data were available at IRSN for a former uranium mine and mill tailings storage site already existing in France that is named La Vaugrasse. And we considered, as you can see here on the right, different scenarios by considering different degradation levels of the layers covering the storage. and the mill tailings due to the impact of erosion with time. So the thickness of different layers are different from the different scenarios. And we also consider the typical house built on the storage. So here on this table, you have more precisely the different depth, thickness of the layers, the soil, the waste rock, and the mill tailings, and the degradation degree of these different layers according to the first scenario with no erosion, the second one with partial erosion, and the third one with the erosion of the entire layers covering the mill tailings. We also used data for the modeling concerning the building. So this is the geometric configuration we chose with some dimensions of the buildings you can see here. And also we chose the geometric configuration of the floating slab, so the interface between the soil and the building, for the modeling with these parameters concerning the dimensions, the thickness of the slab, etc., and the permeability of the gravel and the slab. So this is the model and the data we used for applying our tools according to the three scenarios we also defined. Some other data were also used for modeling the underlying layers of the natural soil, the waste rock, and the mill tailings. So these data were from the direct measurements we have at IURISTEN for the site, the existing site. And some data were also supplemented with data from the literature to have complements for some parameters. And we also used a set of meteorological data, and the depression of the building was calculated by the CSTB by using MATISQIA and was directly used in the models for indoor radon concentration as input information on the basis of this meteorological data. So now, just a word for the models applications. We used two process of collaborative numerical simulation work. The first one is a collaborative process by using tough-to-read and developed at IRSN, and MATISQIA developed at CSTB. So the process collaboration is the following. MATISQIA calculated the depression of the building that was input in tough-to-radon, that calculates the radon flux at the soil building interface, that was used by MATISQIA then to calculate the indoor radon concentration. And the second collaborative process was by using MATISQIA and INDORAD. MATISQIA calculated the depression of the building that was used by INDORAD to calculate the indoor radon concentration. Let's see now. I just added here some references that are also available at on the report we did, and let's see now the results we obtain. Some examples of results we obtained by this first process of collaboration by using tough-to-radon and MATISQIA. So here are some examples of results. On the first line here, you have the results for an example for scenario 2, that is model here, by using tough-to-radon. Tough-to-radon calculates the emanation and the radon transport in the soils until the flux at the interface with the building. And you have here the different radon exhalation flux calculated by for different permeabilities of the mill tailings here. And this exhalation flux, when then used and introduced to MATISQIA application that calculates the indoor radon concentration, you have here the examples of the average annual indoor concentration for the three scenarios we define here. So this is the first example of results we obtained, and I'll give the floor to Alain for the final part of the presentation. Alain, do you want me to share the slides, or you to share your presentation maybe?
But I can go on. Could you continue, Geraldine, and I will comment?
Okay, sorry.
Okay.
So okay. Can you see it?
Yes, but it is your slide. Yes.
Yeah. So.
Okay, thank you, Geraldine. So in CMAT, we participated in this task to modeling of indoor radon concentration with INDORAD model, as said before, Geraldine. It is a model for estimate radon dynamics with time-dependent meteorological parameters, which includes such processes like emanation, dispersion, disintegration, removing from building. Model is based on a systemic approach where the flows of material between compartments are considered. This approach allowed to simplify the mathematical processing and enable to consider together all known sources of indoor radon and reflect temporary variability of indoor radon concentration. It is principally because we don't take into account spatial resolution. A model is based on the above mentioned assumption and other theory of other authors. For example, principal author is Luis Font from Spain, and other one. Please, next one. Geraldine? Yes. His mathematical description of the model. As I said before, it is a compartment model. It is system of ordinary differential equation. The model describes radon as balance of input-output rates, and here you can see equation. First two is for the soil, for upper layer disturbed soil and undisturbed soil. First equation is for radon, indoor radon, and in Greece is differential equation for building material, which was not included in this study, but it can be included. I will not enter into many details, because if you want, you can see details in article published already. You can see here environmental science and pollution research. Please, next one, Geraldine. So model was realized in MATLAB framework and was put in use for case study of high background radiation area sited in Salices El Chico in Spain, in collaboration with University of Cantabria, Professor Luis Quindos, based on the measurements carried out for 2 weeks. And here you can, in the graph, you can see results comparison of the modeling with measurement data during these 2 weeks. Next one. Yes, thank you. In Radonorm project, we put in the use this model for a long, much more longer period, for 1 year, and to calculate indoor radon concentration during 1 year. Model was applied for 2 case studies, Bayroche and Lower Grasse, both of them in France. As said before, Geraldine, the scenario was prepared by IRSN for modeling for building constructed on former uranium mine and mill tailing storage site, Lavagras, like hypothetical scenarios. So firstly, the model was put in use for as a case where we had measurement data to compare measurements with modeling. It was for Bayeroche case study, also in France, where the set of measurement data were available for indoor radon during 1 year and as a necessary meteorological parameter. So in such way, the model was tuned based on geographically close site. The data of measurement were currently provided by RSN and CSTB colleagues. So then fitted model was applied to prognostic case of the scenario Lavagras with hypothetical dwelling built on former uranium mine. Please, next one. So here you can see results of modeling during 1 year. Temporal variability of indoor radon concentration for Bayeroche case study, real case study. Here in red is modeling, and in blue, measurement data. On the right, indoor radon concentration, and on the left, indoor radon concentration, and on the right, radon concentration in the upper layer of soil. Now, next one. And here is results of modeling 1 year temporal variability of indoor radon concentration by Indorad model for Lavagras hypothetical case study. The same on the left, indoor radon concentration and radon concentration in upper layer of mill tailing. Here we haven't any measurements, so only modeling. Next one. And like a summary of this work, we can say that the application of Indorad and French models for modeling the radon transport and indoor concentration for the scenarios showed that the results obtained are in the same order of magnitude. The values calculated for the radon fluxes at the soil building interface and the indoor radon concentration are high and consistent with the scenarios and previous studies. Further investigation need to be made to analyze more in detail these first results and some differences observed between models. And conclusions that the study showed the feasibility to using calculation tools to help the expert radon risk assessment carried out on exposure to radon in buildings. The work saw a lot to compare existing modeling strategies in Europe. The results are intended to be supplemented from simulations carried out on other scenarios that are more representative of a greater number of situations and coverage. Further studies should be allowed to develop more precise and better suited expert assessment tools for radon exposure situations in buildings. And that's all. Thank you very much for your attention and any questions.
Okay. Thank you for the nice presentations. We are
Thank you.
quite late, so only 1 or 2 questions, please.
I have a question in the chat.
Hello, can you hear me?
Yes.
Good morning to everyone. Rajan Bashar from Suro.
There is a question here from the audience. 1 second, Radim.
From the chat, we have a question in the chat from Jean de la Porta. The question is, radium is in a solid would decay in radon gas when times come, but this gas remains contained in the material until it will become stable lead. True or false? Then we read, only measuring the radium on the surface became radon. I repeat the question.
Yeah.
Radium in a solid would decay in radon gas when times come, but this gas remains contained into the material until it will become stable lead. True or false?
I can't understand. It is referred to my presentations or to Geraldine presentations?
For your presentations, maybe, yes.
We developed. I think it was talking about the experimental apparatus to measure radon exhalation rate from the building structure. So we are performing these measurements. It is basically a chamber that is put against the wall, and so you are measuring inside the chamber the radon exhalation rate growth. But we are fitting this initial growth with because we know that we can see that the first hours has a linear trends. So we are fitting this initial growth to have the radon exhalation rate, basically measurement radon 222 concentration growth inside the accumulation chamber.
I've seen that there was a message from Francesco Bucchicchio who said he wanted to answer the question. And there is still a question from online from Radim. Please be very short because we are quite late with the program.
Yeah. Can you please refer, when you're having questions, can you please refer to my part of presentations or the second part, just for brevity?
No, my very short comment on the question made on chat is that as a general question, of course, when radium decays to radon, it depends. It depends if the radium remains there or goes elsewhere, and how far radon goes. Generally, it doesn't stay there. At least not all the radon produced in soil remains there. Otherwise, it will be the case we will not have any problem of radon indoors, at least for radon coming from the soil. So, as a general question, the answer is false.
Okay, thank you very much. Radim, you wanted to have a question?
Yes, thank you. Good morning again. Just very briefly, I was very interested in a technical solution of Syrian equipment or device, especially on the part which is in contact with surface, the wall, and yes, how are you sure that it's sealed and so on? But I understand this is for a longer time than I have now. But my colleagues from Suro are present, so maybe if you will meet them at coffee break or somewhere else, please tell them and they will tell me. Thank you very much.
Yeah, Radim. If you want, you can write me an email because I've made my email address on last slide, and we can give you some detailed information.
Okay, so
okay, thank you very much.
No problem.
I'm sure there will be many other questions, but we have to go on with the program. So thank you, Andrea, and thank all the other speakers from online. And then I leave you for the presentation of the last talk.